SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2, that is Vapor Power System Part 3. So, in the last lecture we have covered the water tube boilers and modern steam generator systems, and these modern steam generator systems mainly constitutes some important heat exchangers like superheaters, reheaters, economizer and air preheaters. Apart from that, there are auxiliary units like fans and stacks. So, these things needs to be discussed. So, in our previous lectures we have mostly covered the important component, that is superheater. So, in these lectures we will follow our attention to the some other heat exchangers which are part of these modern steam generator systems. So, they are reheaters, economizers and air preheaters. So, let us give the brief introductions about water tube boilers, that is nothing but a modern high pressure steam generators. Normally they operate very high pressures at 70 bar for saturated steam and 240 bar for superheated steam. And when you talk about this water tube boilers, they are nothing but the integrations of furnace, economizer, boiler, superheater, reheater and air preheaters. So, in other words, we say that water tube boiler or steam generator is a complex combination of economizer, boiler, superheater, reheater and air preheater. So, if you look at this thermal circuit for a modern steam generator, is that we have a steam drum where saturated steam is generated and it goes to superheated unit, which we discussed in our last class. So, in our lecture today we will be mainly focusing on the important heat exchanger components, that is reheater, second is economizers, third is air preheaters. We will try to find out the need that arises for these components and why they are unique, why they are being used in these systems. Apart from that, we will also discuss about the thermodynamic analysis and heat transfer analysis for these heat exchanger components. Looking at this figure, this is something like that simplified circuit diagrams where these heat exchanger units are placed. So, like beginning with we have economizers, then we have steam drum which gives saturated steam, then we have superheater, then we have reheater unit. But all these heating applications, heating requirements are being supplied, are being given this steam generating unit. So, to summarize, what we have is that feed water from high pressure heater enters the economizer where it receives heat from the outgoing flow gases till it becomes saturated liquid stage and then fed to the steam drum. Then the saturated liquid falls through the downcomer circuit into the bottom header and moves to the riser where the water is partially boiled back to the drum. And finally, the saturated steam from the drum goes to the superheater for further heat addition to the desired temperatures. So, let us think about the reheaters. Now, if you recall our thermodynamic diagram, that is TS diagram. So, the reheating part is normally happens when the steam from its superheated state, that is state 4, expands in the first stage turbine. After expansion to a lower pressure, then steam is further reheated to the 0.6. So, essentially speaking, heat addition process from 5 to 6 is done through a reheater heat exchanger unit. And this reheater heat exchanger unit is nothing but we receive the steam from high pressure turbine and its mass flow rate is m dot s, and steam that goes out at point 6, that is m dot s, that is state 6. And this heat addition takes place from this flue gas, and initially the flue gas temperature is Tg1. After this heat additions, this temperature drops to Tg2. So, thereby and the entire heat addition process is done through mass of this flue gas m dot g. So, our main topic of attention is that we have to analyze this heat exchanger circuit. So, essentially if you look at the heat exchange part in a reheater, like in a superheater we would say that mode of heat transfer can be convection or radiations, but here in reheater, since we are dealing with low temperatures as compared to superheating units, so most of the heat transfer or prime mode of heat transfer is convections. So, analysis of this heat exchanger has to be done through convection mode. So, what we look at this figure, for this reheating unit, temperature, initial temperature of steam is Ts1, and finally steam gets reheated to Ts2. So, that means initially from like this is something like equal to T5, and this point Ts2 is will be like T6, and thereby this heat addition is given from this flue gas. So, its temperature drops from Tg1 to Tg2, and it is a counter flow heat exchangers, and temperature profile for this counter flow heat exchanger is given by this particular figure. So, what we have seen so far is there are, if you say, two temperature difference, that is one is in Ti delta Ti, other is delta Te. So, one end we have the temperature difference at Tg1 as minus Ts2, other end we have the temperature difference as Tg2 minus Ts1. So, from this temperature differential one can define logarithmic mean temperature difference. Now, once you find the LMTD, then we can find out, link this heat transfer through these expressions that involves overall heat transfer coefficients, outer surface area and delta T LMTD. But this heat comes through convections. So, you can make a heat balance equations that talks about the heat rejected by flue gas is getting added to the steam. So, one way for this T5 corresponding enthalpy is H5, and for T6 corresponding enthalpy is H6. So, thereby we can find out what is the heat transfer into the steams, and what is the heat transfer that goes out from the flue gas, that is m dot d g, because this is a gas phase. So, it is m dot g Cpg into Tg1 minus Tg2. Once you have these expressions, then we can link these things to the outer surface area, that is n times pi d0 into L, and we also from the steam flow rate expressions that can be linked, because steam goes through the tubes which have inner diameter di and number of tubes is n. So, you can find out area, what is the effective area, and from area into density, that is of the steam, and mass and velocity of the steam. So, knowing this, we can solve this problem of counter flow heat exchanger unit and to get the desired parameters. And effectively, normally we start with the calculations of heat requirement for this steam that is being supplied to through the flue gas. Then we have to, this heat has to be linked to the geometrical aspects of the heat exchanger, and that mainly deals with the outer area of this tube, and this outer area will give you this how many number of tubes is required, what is would be the length of the tube, all these things can be calculated. Again, another mode of heat exchanger that is used in the steam generating unit is the economizers. So, if you can see this modern steam generator, economizer is the location which is in the steam generator unit. It is mainly used to utilize the unwanted or exhaust gas from the flue gas. Exhaust, I mean the heat, waste heat from the flue gas is being used in an economizer unit. And what is this purpose? The economizer uses the energy of the waste heat of the flue gas to preheat or to heat the liquid water to the saturated liquid, and that enters to the steam drum. So, the word economizer historically is used because the discharge of such high temperature gas would cause huge loss of exergy and efficiency of the plant. So, that is the reason it has been advisable that the waste gas available at around from the flue gas at around 350 to 500 degree centigrade should be utilized. And one such unit is, of course, it is being utilized in superheater and reheater. Other unit also you can be utilized it in the economizers. So, an economizer is a heat exchanger that raises the temperature of living high pressure feed water heater to the saturation temperature corresponding to boiler pressure or entry to the steam drum. So, this is also an essential requirement for a modern steam generator unit. So, the analysis of the economizer is almost the same thing, but what we have done for reheater and superheater unit with convection mode of heat transfer. Here also it is mode of heat transfer is convection, but only difference is that for here heat comes from the flue gas, that is that temperature drops from Tg1 to Tg2, and feed water temperature rises from such feed water temperature to the saturated temperatures. So, only this difference is there. For entire and similar analysis also we need to calculate the logarithmic mean temperature difference for a counter flow heat exchanger mode. Then we have to find the heat transfer to the feed water through this energy balance equations. Then you have to use this equation or link these equations to the tube geometry by through this overall heat transfer coefficients, outer surface area and LMTD. So, once you know this, finally our end result would be, or end requirement would be, what is the surface area requirement, what is the number of tubes, what is the length of the each tube, for which the water has to be inserted into the economizer unit. Then next requirement is the air preheater. So, it is another type of air preheater. Normally they are of two types, recuperative type and regenerative type, and these they normally use the hot gases, hot flue gases, and then to rise the temperature of air. Now, question arises, why you require the increase in the temperature of air? Normally for combustion purpose point of view, like if you can see here, just below the steam drum or header and downcomer unit, we require the fuel and air should enter. So, that air is also sufficiently high, is required for appropriate combustion. Now, when this air is being fed, so it is better that you preheat the air by using the flue gas. So, for that thing we require an air preheater, and there are two types of air preheater, one is recuperative type, other is regenerative type. So, in a regenerative mode, normally what happens, the heat is stored by an intermediate unit. So, that intermediate unit could be a ceramic matrix or a steel unit, which is nothing but it will act as a energy storage medium, and then as and when required, the stored energy can be utilized to preheat the incoming air, and this maximum temperature we can go up is up to adiabatic flame temperatures. But in the steam generating unit, this is not an advisable option. So, it is better that you use the other mode of heat exchanger, which is called as recuperator. So, recuperator is a heat exchanger unit in which energy from the steady flow of hot combustion products or flue gases is transferred to the air supplied for the combustion purposes. So, basically this air preheater unit in a steam power modern steam power generator is a recuperative type air preheater, and again it operates in a counter flow heat exchanger mode. So, this counter heat exchanger, but its design is little bit different. So, this unit normally uses a tubular type. So, this is nothing but a tubular type air preheaters. So, basically the tubular flow heater means that we have tubes which allows the flow gas to pass through various tubes, and for better circulation of air, that means the passage of air is made in such a way that this air gets maximum interaction with the flue gases to enhance its temperature from TA1 to TA2. And for a given mass flow rate of air, there is also essential requirement of mass flow rate of flue gas. So, analysis is again simple type of heat exchanger unit, where only difference is that energy comes from the flue gas, only air is heated from TA1 to TA2. So, now to give some standard numbers, normally these air preheater units receives flue gases at around 320 to 420 degree centigrades, and the gases are cooled up to 130 to 170 degree centigrades. Normally that means Tg1 and Tg2 are fixed in this range. Then air temperature, which is normally atmospheric air, which gets preheated and to up to maybe 90 degree centigrades, or it can go up to 260 degree centigrades. So, depending on the what temperature of flue gas is in. So, by using this, that means we can have a typical fuel saving of 4% for preheating of air to 90 degree centigrade, and you can get up to 12% fuel saving when you use the preheater to up to 260 degree centigrades. So, in addition to fuel saving, the preheated air is also requirement for pulverizer coal for drying purposes. So, like again for coal firing unit, we also require dry coal to be entered into the furnace. So, that is also used, preheated air is also another requirement, additional requirement for the power systems. So, analysis is also similar to any heat exchanger unit, and that operates with convection mode of heat exchanger, and here we need to do this energy balance first, that is a heat flow into air preheater, that is Q dot APH. We can do energy balance, that is heat rejected from the flue gases is getting added to the air to increase its temperature from TA1 to TA2. Another expression we can find out with respect to this heat transfer is by linking this with respect to geometry of the preheating unit through overall heat transfer coefficients, outer surface area and LMTD. Here also LMTD can be calculated in the similar manner as we discussed previously. And of course, we can also link what is the gas flow rate. So, it is not steam, it is gas flow rate mg dot for the flue gases, and of course, from these expressions we can find out, by doing this analysis we can find out A0 surface area requirement, number of tubes and length of the each tube. Okay. So, next till this point of time we are covering only heat exchangers components of a modern steam generator. Now, we will look into some auxiliary components. The other auxiliary components, that is there are fans. So, fans is, we all know that conventional fans, they have a certain pressure differential, and with respect to steam generating unit we require fans. Why do we require fans? First thing, we need to push the air into the system, and air requirement is of many folds, like we need fuel air requirement at the furnace stage itself. So, that means we need to push the air. So, to push sufficient amount of air and to create a pressure differential, we require a fan. Now, once this is one requirement, second requirement is that once the combustion happens, combustion takes place, energy release has been take place. So, it generates the flue gas, because fuel and air when mixed, it at the end of the combustion it generates the flue gas, and the flue gas has to be taken out from the systems. So, again we require some kind of fan which require to pull it out from the system. So, basically the role of fans is to assist the large steam generator unit to push the air into this unit through a fan called as forced draft fan, and also pull the combustion gas out. So, that means for that reason we require an induced draft fan that takes this flue gas out from the systems. So, push and pull concept is very useful for a steam generating unit, and it is one of the most requirement for the system. So, there are basically two types of fan, forced draft fan and induced draft fan. So, they should overcome the total air and gas pressure losses within the steam generator. Many modern steam generator used forced draft fans that are placed at the air entrance to the preheater and put the entire system till the stack temperature under positive gas pressures. So, they are forced draft fan. So, that means the system is already in the gauge pressure, which is in a pressure form, already the unit is in a pressurized unit, because we use the forced draft fan to push the air into the systems. And these forced draft fan, they handle only cold air from the atmosphere. So, because of this reason they have advantage like low maintenance problems, less consumption power, less capital and operating cost, but the only difference is that since it is always pushing the air into these systems. So, the unit is already under pressure, and we call this as a pressure furnace. But there are other category of fans which we call as induced draft fans. They are located in the gas stream between air preheater and the stack, that is stack side is here and air preheater unit is here. So, they are essentially the induced draft fan takes the or pulls the combustion products out from the systems towards the stack. So, thereby when you say induced fan design, they handle hot gases, that includes original air also, because in the circuit also some of the original also gets pulled away, and also gas equivalent fuel, which means power requirement is greater. So, induced draft fan power requirement is higher than the forced draft fan. But in a balanced draft steam generating unit, what we have? We have a forced draft fan as well as induced draft fan, and they operate in a such a way, because they know their role in such a way that system is under balanced draft. So, the forced draft will push the air and induced draft fan will pull the combustion product out of the systems. And since for large power generating plants, the typical fan size should handle about 700 meter cube per second, and but of course, very high volume flow rate, but almost a very low pressure like 0.15 bar is pressure difference is there, is sufficient to handle this flow rate. But of course, since the plant is continuously running, so this fans also runs 24/7, and so their life period is something about 1.5 years. Now, coming back the type of fan. So, either it is a induced draft fan or forced draft fan. They are actually two types, one is centrifugal type, other is axial flow fans. So, the centrifugal fans, as you see this figure, these gases are accelerated radially. So, gases are accelerated radially. If you look at this particular figure, the centrifugal blading, we shows that if you have a absolute velocity air leaving the blade is V, blade velocity is Vv and relative velocity is Vr, then we can form a velocity triangle involving Vb, Vr and V. So, one way we can say that when you say forward blading, you can see this velocity triangle diagram, but when you have flat blade, then we can see the direction of Vr and Vb and absolute velocity. Then we have, when you have backward curved blade, then we can see this orientation of Vb and Vr and V. So, thereby this makes a requirement whether when you push the air, we normally require forward blading, when we pull the gas out, we normally require backward curved blades. So, that way blade design through centrifugal blading will help us in deciding whether by making decision to use the forced and induced draft fans. But there are other category of fans which is normally conventionally we use similar to our desk fans, in which the gases are accelerated parallel to the rotor axis. So, in a conventional desk fan, when you are sitting in front of it, you can see the feel of air hitting on your body because the air is being directed axially through its blading. But these axial fans have high efficiency over wide range of loads than constant speed fans, but they incur very high capital cost. But one way, best way is that we should use a centrifugal type of fan. Normally the standard characteristics curves like what point, what is the flow rate and what is the power requirement, what is the pressure rise, all sorts of things is governed through the characteristics curves of fan, which that means we should this particular curve shows if you have fan parameter like static pressure rise, so normally it increases with flow rate and drops subsequently. Power increases, then subsequently after certain flow rate it drops. Static efficiency increases initially, then drops. So, basically the characteristics curve, that means we should meet a balanced point of range of flow rate for which the fan should be regulated to operate. So, this is the range of volume flow rate that we should ensure to have maximum potential or maximum ability for to run to have this combined effect of static pressure rise, power requirement and efficiency. So, basically whether you use backward curve band or forward curve band, but I find at the end of the analysis we require what is the power required by the fan, which is W dot F, and that can be calculated by for a steady flow thermodynamic systems, and the power requirement per unit volume, unit mass we can calculate is integration of V dP. So, V can be taken out from this integration because we are handling the gas which is typically incompressible in nature, and this gas is being felt a pressure differential of delta P, and from this we can calculate the power. Of course, we can introduce at what efficiency fan operates, that is efficiency of the fan. Then this power requirement can be related to two types of pressure drop. One is static pressure drop, other is velocity head or static head or dynamic head or velocity head. And in terms of the static head, we can bring this pressure differential to a unit of meter. So, a velocity head we can obtain from the velocity of the steam or gas, then we can use the static head based on the static pressure difference, and that pressure difference is nothing but losses that occur at various components of the steam power unit. The next segment of our discussion is stack. Normally, if you have seen this particular figure, here this particular unit we that means when the flue gas comes out from the power steam generating unit, it goes to the stack. So, let us see what does this stack means, and if you see this particular figure, you can see the flue gas that comes out from the stack, and this stack is nothing but a very high rise structure of certain height h, and the flue gas that comes out that means ideally speaking that flue gas has to go out at a larger height, and when it goes out, this flue gas try to expand in the atmospheric medium. So, you can see there are plumes coming up, and when they it is like a expansion of this free jet in an open atmosphere, and for which we can make a concentration profile from the plume, and through this expansion process say they try to disperse in the atmosphere. So, essentially the role of stack in a fossil fuel power plant has two major functions. One is assisting the fan to overcome the pressure losses, because this itself gives a pressure differential from the higher at a larger height with respect to the atmospheric height. So, this is one thing. Other is most important thing to help the dispersing of combustion gases efficiently into the atmospheres. So, essentially this driving pressure between these two is density difference of atmospheric and rho s bar. Rho s bar means is average stack density. Stack density, that means whatever gas contains within these things. So, they are taken as the average gas density, and this atmospheric density is related to atmospheric pressure, temperature and its gas constant. Even for stack density, it is with respect to stack pressure, gas constant of the stack and average stack temperatures. So, they can be related to ideal gas equations, and ultimately we can frame this requirement of pressure differential that happens for the stack. So, this is nothing but your first objective, that is assisting the fan to overcome the pressure losses. This additional pressure losses, I mean if you use the stack, ultimately we will be trying to reduce the fan power. But the second main important objective of the stack is the dispersion of flue gases. What happens is the flue gas disperse into atmosphere, that means dispersion of gases into atmosphere is defined as the movement of flue gases horizontally as well as vertically, and their dilution by the atmosphere. The horizontal motion is nothing but the existing wind velocity, that means we can see that higher things, we can see the wind velocity at Vw, and this is horizontal velocity, and this is gets assisted based on the direction of the wind. Other part is the vertical part, and vertical component is also governed by what flow rate or what is the momentum it has achieved when it comes out of the stack. So, the combined effect is the nothing but the formation of a plume. So, what is done is that a plume high rise is defined, which is delta H, and this is above this actual stack height is H, delta is in additional height which is called as plume rise, and it is defined as the height of virtual point source above the stack, which is obtained by extending the lines of dispersion backward. So, that means the flue gas lines of dispersion are these two, and when we extend them backward, we arrive at a point what is called as point source, and from this point source we can measure this height above H, which is nothing but your delta H. Now, to analyze what is this delta H, we need to use some analytical methods that utilizes momentum terms to account for the vertical momentum of the gas caused by the stack exit velocity and buoyancy, because the dispersion takes place through buoyancy or density difference of the stack and atmospheric air. So, there are different models or correlations has been used, but in this lecture we am just covering that to find this effective stack height, we have to find this actual H, which is this, and delta H, and delta H is nothing but your plume height, and it is modeled through Briggs correlations through these expressions 114 C f to the power 1 by 3 divided by Vw. Now, here the terms associated with this is first term is F, which is nothing but the buoyancy flux, and that is nothing but we can expression is G Vs times d square Ts minus Ta divided by 4a, and second term is called as a dimensional temperature gradients, which is expressed in this form like 1.58 minus 41.4 delta theta by delta z, which is nothing but air potential temperature gradient, and this value ranges from minus 0.001 to 0.013. So, it is better that we assume any value of this delta theta by z from this range, and when there is atmospheric stability, that means there is no turbulence, no disturbance. So, this delta theta by z is 0. So, once you know this, then you can calculate this delta H. Okay. So, this is all about the important primary units of heat exchangers and auxiliary units that involves fans and stacks. So, we will try to solve some numerical problems based on our discussion in this lecture. So, the first problem deals with an economizer, and typical circuit diagram I have explained, it is a counter flow heat exchanger. So, its main purpose is that feed water temperature increases to the saturation temperatures, and it is done through the flue gases. So, from this figure and given data from here, what we have seen is that we can put a condition, that is state 1 for the feed water and state 2 for the saturated water that goes out. Now, from the data that is given for feed water, so it the 140 bar 170 degree centigrade flow rate at this, and it is heated till it becomes saturated liquid. So, we have to use steam table first thing, and for the steam table we have to use state 1. The data is 140 bar 170 degree centigrade. So, it is a high pressure feed water. So, for this thermodynamic states, from the steam table we can find out H1 as 1571.1 kilojoule per kg. We also require specific volume V1 0.001611 meter cube per kg, and for state 2 it is nothing but 140 bar saturated liquid. So, from this data we can find out T saturated is 336.7 degree centigrade, Vf at this stage we can 0.001144 meter cube per kg, and of course, you have enthalpy is 719.2 kilojoule per kg. So, first thing we have to use this heat balance equation. That is Q, this is economizer, is m dot s H1 minus Hf is equal to m dot g Cpg Tg1 minus Tg2. So, we have m dot s is equal to 580 kg per second, m dot g 1260 kg per second, Cpg 1.12 kilojoule per kg Kelvin, and then Tg2 460 degree centigrade. So, putting this we also have H1, Hf, everything is there. So, this equation it can be solved for. So, what is unknown? Tg1 is unknown. So, you can find out Tg1 minus 733 is equal to 350. So, this will give you Tg1 as 1083 Kelvin or 810 degree centigrade. So, basically now you come back to these data points. We all know this Tg1, Tg2, T saturated and Tfw. So, you can find out what is delta Ti, that is Tg1 minus T saturated, that is equal to 810 minus 336.7. So, this is 473.3 degree centigrades. Then delta T E, that is Tg2 minus Tw. So, this is 460 minus 170, data is given. So, it is 290 degree centigrade. So, from this we can find out what is delta Tm, which is delta Ti minus delta Te divided by ln delta Ti by delta Te. So, from this we can say what is delta Tm is equal to 374 degree centigrades. Now, once we have known this, then subsequently this Q can be related to U0, A0, delta T, LMTD, right. And what is this Q? Q is nothing but m dot s H1 minus Hf, that is 580 into 1571.1 minus 719.2. This is this much kilojoule, and U0 is given as 68 watt per meter square. So, and LMTD is 374 degree centigrade. Then from this equation all data are known. So, from this we can say A0 except A0 would be Q by U0 delta T LMTD. By solving, inserting the values, we say A0 is 22019 meter square. Now, once you know this A0, then we can find out what is this A0 is number of tubes n pi d0 into L. So, here two unknowns are there, what one is n, other is L, and d0 is given as 65 millimeter and di is given as 55 millimeter. To find this, then you have to recall these expressions. What is mass flow rate? M dash S is equal to number of tubes into area pi by 4 di square multiplied by Vw divided by specific volume. So, water velocity Vw is given 1.2 meter per second. Specific volume data we have like 0.0100 from this steam table data, 0.001611 meter cube per kg. So, di is 55 mm. So, putting this value we get m dot s, and m dot s is mass flow rate of steam 580 kg per second. So, this is known, Vw known, Vf known, di known. So, this will give you n is equal to 328. So, inserting values you have n is equal to 328, that means number of coils needed is 328. Then from these equations L can be find out A0 by n pi d0, that is 22019 by 328 into pi into d0 is 65 into 10 to the power minus 3. By solving this, we can get L is equal to 328 meter. So, equal 328 long tube and number it is not 328. So, this can be evaluated to find this L. So, number of tube is 328 and length of the tube can be evaluated from these expressions. The next problem is that is in connection with this question 1, that is for steam generator unit, it uses an air preheaters. So, essentially speaking, we need to take some data from our previous question to solve this problem. So, for the steam generator for the question 1, we use a tubular air preheater and following the economizer where the flue gas flows through the tubes and cool to 160 degree centigrade. So, same problem is here, but here it you have air entry at TA1 temperature mass flow rate and air goes out m dot A and TA2. So, for solution of this problem, we have to again use the similar approach, which says for air we can take the data from this question, that is Ti 35 degree centigrade, To not given, we have to find out m dot A is equal to 1150 kg per second and flue gas from question 1 data, from the question 1 data we have Tg1 460 degree centigrade, Tg2 160 degree centigrade. We have also Cpg 1.1 kilojoule per kg Kelvin and m dot g 1260 kg per second. So, you again here use energy balance between flue gas and air. We says Q is equal to m dot A Cpa T O or minus T I, that is equal to m dot G Cpg T G1 minus Tg2. So, all these numbers are given, m dot G, m dot A all are given. So, only unknown is To. So, from this equation we can find out To is equal to 395 degree centigrade. Once you know To is like O and this is I. So, To and Ti is known. So, from this we can find out voltage delta Ti is equal to Tg1 minus Tgo, that is 65 degree centigrade, delta Te is equal to Tg2 minus Ti, that is 125 degree centigrade. So, you can say delta T LMTD is equal to delta Ti minus delta Te divided by ln delta Ti by delta Te. By inserting the value we get delta T LMTD is equal to 92.3 degree centigrade. So, we know LMTD, then we can link this Q U0 A0 delta T LMTD, that is equal to, use this equation, one of the equation like 1260 into 1.1 Cpg, then depth temperature difference is 460 minus 160. Now, from these equations we also have U0, inner and outer diameter are given, overall heat transfer is 30. So, U0 is 30 watt per meter square Kelvin. So, this will give you A0 is equal to 150612 meter square. So, once you know this, then you can find out, we have this A0 is nothing but n into pi d0 into L, that is length of the tube, outer diameter, number of tubes. So, we have A0 already calculated, that is 150162 meter square, d0 is given as outer diameter 65 mm, di is also given 60 mm. So, di is required because we need to find what is n. So, to do that we have to recall this expression, mass flow rate of flue gas, which is n into pi by 4 di square, because flue gas enters through a tube of diameter di, and Vg velocity of the flue gas, specific volume of the flue gas. So, for specific volume of flue gas we can use as ideal gas model R Tg1 RT by P. So, R is for flue gas, it is 0.287 kilojoule per kg, see that value, and Tg1 is 460 degree centigrade plus 273, pressure is mostly atmospheric 101.325. So, this will give you Vg1 as 2.07 meter cube per kg, and velocity of the flue gas is 12 meter per second. M dot G This is 1260 kg per second. So, in this equation now we will be able to find out what is N, and that N is equal to 1260 into 2.07 into 10 to the power 6 into 4 divided by pi 60 square into 12. N is 76861. So, this is the number of tubes required, and for this number of tubes, so L can be obtained as A0 by N times pi D0. So, 150162 divided by 76861 into pi into 65 into 10 to the power minus 3. So, L would be 9.56 meter. Okay. So, this is the second problem, which is based on air preheater, and third problem is based on the stack. So, I mentioned the modern steam generator unit uses a stack, and that stack height is, or effective stack height HE is equal to actual height plus delta H, and delta H is nothing but plume height and this is covered through Bragg's relations, and that is 114 C F to the power 1 by 3 divided by VW. So, essentially speaking, we are looking at the stack, which is original height is H, and this plumes comes up, and somewhere we have a virtual point where the point meets virtual point, and this is your delta H and H, and this height is HE. Now, let us see what are each term is all about. So, first term we calculate F is nothing but buoyancy flux, that is G times V S square D divided into T S minus T A divided by 4 T A. So, T S is given as 100 degree centigrade, that is 373 Kelvin. T A is 5 degree centigrade from the data given, and this is 278 Kelvin, and we have m dot S flue gas 1000 kg per second. So, velocity can be obtained as V S, that is m dot S divided by rho S into A, and rho S is nothing but P by R T S. Pressure is atmospheric 101325. Flue gas, value of R for flue gases is 287. Temperature of the stack is 373. So, this will give you rho S as 0.9465 kg per meter cube. So, once you know rho S, we can find out V S, velocity of the stack gas. V S is 84 meter per second. Of course, we are known with wind speed VW, which is given as 14 meter per second. So, one can find out F is equal to 9.81, V S is 84 square, stack diameter D is 4 meter, and H is equal to 220 meter. T S minus T A 373 minus 278 divided by 4 times T A 278. So, this value is 1126.4 meter to the power 4 second cube. The next term which we are going to find out C. C is nothing but non-dimensional term given by the expression 1.58 minus 41.4 delta theta by delta z. Delta theta by delta z value, let us approximate to it a value as 0.005 for an atmospheric stability conditions. Now, when you assume this value, C is equal to 1.373. So, essentially speaking, in this equation we have all the parameters. So, we can find out this plume height is equal to 114 into 1.373 into f to the power 1.3, that is 1126.4 to the power 1 by 3 divided by wind velocity 14 meter per second. After evaluating, this value would be 116 meter. So, plume height is 116 meter, effective height would be 220 plus 116, that is equal to 336 meter. So, this problem demonstrates how the stack height can be calculated for a steam power generator unit. So, with this I conclude for this lecture today. Thank you for your kind attention.